Okay, so sorry I can't be there to go over this review with you in person, but I'm going to go through my answers to each one of the questions on the Energy and States of Matter unit review. Please make sure that you watch all the way through, take any notes, make any changes, corrections that you need to. If you should have any questions about any of this, you're going to have to email me, and I will try to respond to those emails this evening in between our classes up here at Tracer tomorrow. So, beginning with the first section, which is all about energy. Question 1, draw energy bar graphs to account for the energy storage and transfer in the following scenario. Water at 100 degrees Celsius is cooled down and frozen into ice cubes at -5 degrees Celsius. So here we have our LOL diagram. We have water that is right at 100 degrees. So it's not boiling, but it's just at that temperature. And we're going to start removing energy from that. So we're going to go all the way down to -5 degrees Celsius. So that's going to be a big decrease in the thermal energy of matter. So thermal energy is directly related to the motion of those particles. So in my example here, I went from 4 bars of thermal energy down to 3. And again, the total number of bars that we go down by for thermal energy is kind of irrelevant. We do want to be able to model that the thermal energy is overall decreasing. We're also going through a phase change because we can't just go from 100 right to -5. We're going to be freezing at 0 degrees Celsius. So freezing means you're going from the liquid state to the solid state. And so that's going to be a decrease in the interaction energy. So we can see that going from 2 bars, which we use to represent liquid, to 1 bar that represents solid. So for my diagram here, I started with 6 bars worth of energy. I ended with 2. And so I have 4 bars of energy leaving the system, which is the water, via heating. So that's why the Q is there. Part B, draw particle diagrams for all states of matter described in the above scenario, and then verbally describe the differences. So we've got the water on the left-hand side, and we got the ice on the right-hand side. Water at 100 degrees Celsius. Water, those particles are spread out, disorganized, moving very quickly, especially at 100 degrees Celsius. You're going to have a lot of thermal energy, so there are big whooshies there. On the other side, though, ice. Ice is a solid. In a solid, the particles are much more organized. So you can see the orderly arrangement there. And then we've got the arrows indicating the oscillations back and forth. They're not free to move around like they are in the liquid, but they will vibrate in place, because as we know from kinetic molecular theory, particles are in constant motion. So there we go. Moving on to the next section, where we're tying together kinetic molecular theory and energy. We're looking at a heating curve. Now this heating curve is a general heating curve. You'll notice on the temperature scale that I do not have specifically any temperatures there. It says MP and BP. MP stands for melting point and BP stands for boiling point. For any given substance, it can be a solid, it can be a liquid, or it can be a gas. The temperature at which it transitions from solid to liquid is different for different substances, and the temperature at which it goes from liquid to gas is different for different substances. So this graph, this chart, could be used as a heating curve for any substance. Okay, so this thing is completely filled out. Questions 2, 3, and 4. Table which phases are present at each portion of the curve on the previous graph, including states of matter. So starting in the bottom left-hand corner, lowest temperature, we have the solid state, and the temperature of the solid state would increase until we reach the melting point, at which point we're going through the phase change, which would be melting or freezing, depending if we are adding or removing energy. After it completely melts, we have the liquid phase. Temperature of the liquid phase is going to increase until we hit the point where the liquid would start to vaporize or condense. So we have the next phase change at that boiling point, and then above the boiling point, the substance is a gas. Okay. Question 3, label the sections with the kinetic energy or thermal energy of the sample is changing, and then the interaction energy. So starting with the solid state, we see that the addition of energy is changing the temperature. It's not changing the state of matter, just the temperature. And so if there's a temperature change, the particles are moving faster. That means thermal energy. So you see delta ETH, change in thermal energy. When we get to the phase change, melting and freezing, now we're changing the interaction energy. So we're adding energy, which is going in specifically to overcome the force of attraction between particles to allow them to separate enough that they can start to transition into the liquid state. Once we're in the liquid state, once again, we have delta ETH for change in thermal energy. Thermal energy is increasing as the particles begin to move faster. And at some point, we're going to reach that boiling point temperature. And now, once again, we're changing the interaction energy. So we're overcoming all the forces of attractions between the particles, allowing them to separate and go into the gas phase. And once we're in the gas phase, all those particles have completely overcome the forces of attraction between them. The particles are completely independent and separate. They're in the gas phase. And we can continue to increase the thermal energy of those gas particles. Question 4. Next to each part, write out the equation that you would use. Well, when we're changing the thermal energy for solid, liquid, and gas, the equation is Q, or heating, equals mass times heat capacity times the change in temperature. I have to remember that each state of matter has its own unique heat capacity value. So for instance, water, heat capacity of the solid is 2.1 joules per gram. For the liquid water, it was 4.18 joules per gram degree Celsius, and for the gas it's like 1.9 joules per gram degree Celsius. As far as the phase changes go, the equation's a little bit different. Q equals mass times the heat of fusion for the equation when we're melting or freezing. Okay, we'll talk more about what heat of fusion is in just a second. When we go through the vaporizing condensing stage, we have Q equals mass times the heat of vaporization. So we've got that. Just remember in those two equations for the phase changes that the heat of fusion and the heat of vaporization is positive when we're melting or vaporizing, but that value needs to be negative when we are freezing or condensing. And it's negative because the energy is being removed. We don't have to worry about things like that with the solid, liquid, and gas states in those equations because the negative sign will pop up due to the change in temperature being negative or positive. And then question 5 says, what is the physical meaning of heat capacity, heat of fusion, heat of vaporization? Well, the physical meaning for heat capacity, the amount of energy needed to change the temperature of 1 gram of substance by 1 degree Celsius. It is a new unique value for every substance and state the substance is in. So the heat capacities for water in the solid, liquid, and gas states are different. And the heat capacities for solid water, liquid water, and gaseous water are different than solid, liquid, gas of another substance. So new, unique, depending on the substance and what state it is in. Heat of fusion, the amount of energy to add or remove from a substance for it to transition between solid and liquid states. And again, that is a unique value for every substance. Different substances, the particles have different forces of attraction between them. And so it's going to take differing amounts of energy. So that's a known value for different substances, but remember it is unique for each substance. As far as the heat of vaporization goes, heat of vaporization is the amount of energy to add or remove from a substance for it to transition between liquid and gas states, and once again is a unique value for every substance. The heat of fusion is typically a much smaller value than the heat of vaporization. Like in water, heat of fusion is 334 joules per gram. It doesn't take as much energy to just pull the particles apart enough that they can start slipping past each other, like it does for it to go from liquid to gas, where you have to completely overcome all of the attractions between particles and have them go off into the gaseous states. Here we have questions 6 and 8 because they go together. Question 6, now we're into the energy calculations. For question 6, we have 150 grams of water at negative 10 degrees Celsius, and then the final state is 150 grams of liquid water at 0 degrees Celsius. So if we look at that on a little heating curve, we can see we start at negative 10 degrees. We're going up to 0. Once we get to 0, we're going to be melting. Excuse me, and then the scenario ends once all of the solid has turned to liquid. As far as describing the energy changes taking place, first energy is added to the system, increasing the thermal energy of the ice. And we can see that from the temperature going up. The particles are going to start shaking and vibrating more. Secondly, additional energy begins to increase the interaction energy of the ice. This begins when the solid reaches 0 degrees Celsius or its melting point temperature. the increase in interaction energy causes the solid to turn into a liquid again, overcoming some of those attractions between the particles just enough that they're able to slide around each other and become disorganized and more like a liquid. Question 8 was then asking, how much energy does that change take? Well, in step 1, we had the warming of the solid. So Q equals mass times heat capacity times the change in temperature. So we have 150 grams. The heat capacity of the solid is 2.1 joules for every gram degrees Celsius, and the change in temperature, the final temperature over this stage, the final temperature of the solid is 0, because once we get to 0, it's going to start becoming a liquid. And the initial temperature was -10. So 150 times 2.1 times 0 minus -10 would be +10. To 2 sig figs, that gives us 3,200 joules. Now for the change, the phase change, we have Q equals mass times heat of fusion. Heat of fusion here is going to be positive because we're adding the energy in. So 150 times 334 gives us 50,000 joules. Also to 2 sig figs. If you wanted to write it as 2 sig figs, you could put 5.0 times 10 to the 4th joules, but it's 50,000. And if we add it all together to 2 sig figs, we get 53,000 joules. Otherwise, 53,200 joules. And then the last set of questions. Question 7, we have 200 grams of gaseous water at 100 degrees Celsius. And then the final state, half of the water is frozen at 0 degrees Celsius. So on my heating curve here, we have the condensing. So the gaseous water, the steam is right at 100. So if we remove any energy, it's going to immediately condense. And then the liquid is going to cool down. And then we're only going to freeze half of the water, not the whole thing. So first, energy is removed from the gaseous water. Since it is at the condensation point, this lowers the interaction energy, allowing the forces between particles to pull them together, forming a liquid. Secondly, a lot of energy is going to be removed, decreasing the thermal energy of the now liquid water. Once it decreases to the point where we have 0 degrees Celsius, more energy is removed from interaction energy, allowing the particles to form the solid. Again, only half of it, but still going to be forming into a solid. So we had 3 different parts to that heating curve. So we got 3 different calculations to perform. First, we're going to be condensing all that water vapor. Q equals mass times heat of vaporization. Here, the heat of vaporization is negative because we're removing that much energy. 200 times 2,260 gives us negative 500,000 joules. Cooling the liquid, now we've got the temperature change for that liquid water. We have 200 times 4.18 times negative 100 gives us negative 80,000 joules. And then finally for freezing, we have Q equals mass times heat of fusion. Again, the heat of fusion here is negative 334. So we have 100 grams times negative 334 gives us negative 30,000 joules. Just to note, this little scribble that I just circled right there, that's nothing. I just accidentally wrote something there and I was scribbling it out. So all the energy together that's being removed comes out to a total of negative 610,000 joules, or if we rounded it off to the right sig figs, negative 600,000 joules. So that is it. That is going through all of those questions. Please feel free to go back and review, watch again, listen again. But if you have any questions, please email me. I will do my best to get to those this evening. Again, we are in class until about 4 o'clock, and then in class again from 6 until 8:30 at night. So I will try to get to them between our afternoon and evening classes. If not, probably won't hear back from me until around 9 p.m. tonight. And I apologize for that. It's just the schedule that we're working with. So anyways, there's the review. Feel free to, again, go back through that, talk with classmates if you want to review anything. And otherwise, the Energy and States of Matter exam is tomorrow, and good luck.